want to begin here, let's talk a little bit. Everybody should have had basic electricity. Some of you may have had components. Some people may have worked more throughout their life with electricity. But, just let's lay down some parameters here. First of all, they tell us in our text that basic electricity is the movement of electrons at the atomic level, right? And so we have materials which we call conductors, or what we really mean is better conductors than those things. And they're atomically structured where they're electrons, which are negatively charged particles of an atom. You have a nucleus, you have protons, positive charge, and you have electrons. Whenever the structure exists where the electrons are kind of left out of the atom, kind of hanging out there loose. And what we mean is, say we've got a certain number of protons and electrons, we can't get them all. And so as we get to more and more, our atomic structure comes up with more protons, more electrons. We build it into shells. And so when one is full and we start again, that means like one electron's hanging out the new shell. And we fill that shell up, and so we find that gold and silver and aluminum and copper and these things all share that, where what we'll call their valence electrons are hanging out there, and they're easier to repel and attract and to displace. And so basically what electricity is, this energy, it has the ability to move those electrons from one electron on the atomic structure to the next atom. And it's just a movement of them. Okay? It's not magic. We're just moving electrons. Now, when we talk about electricity for our HVAC work, we usually have some parameters. Most residences are put together what we call single phase power. Now, you say single phase power. Yes, there are two lines of single phase power delivered to most houses. We look at power, we rate power, and we measure power, first of all, in a term called voltage, which is a pressure. It's not an amount, it's a pressure. And so the way they generate power to us, they step power down to us, but it's easier for them to bring it in the way they do. And what most residents have are two hot lines of power. Okay, two hot lines of power. And this power is usually, typically, you might hear somebody say, I got a 115 volt circuit, or some people might say I got a 120 volt circuit or 125. It depends on who's manufacturing your electricity. Is it Alabama Power? Is it a co-op? Is it something like that? They might be a little different. That's a voltage, and they would bring two of those in that have been generated at different time frames. So when we look at a generator or an alternator, depending on how you want to look at it, got some new pens to go with the glossy cover there. And so a generator is very similar to a motor, electric motor. So we take a magnet, and everybody's played with a magnet before. You have two different ends, maybe a north and a south. Some people may call them negative and positive. And if you have two magnets, you put them together, you got your likes and your dislikes. Some repel, some attract. But if we look at this magnet here, and if we put a piece of metal that has iron in there, like steel, it'll line up with this thing, right? We've all played with magnets. Well, they find if we take this thing here and we spin this, and I'm going to call this a conductor because it's conductive to magnetism. If I spin this inside of a magnet, it'll produce electrons to flow if we've got a path. So if I take a coil, a wire, I take a copper coil, come around here, we start spinning this, whether we spin it with a hamster or a horse or steam or whatever, it'll cause electrons to flow out this conductor. That's how they're generating power. And they're going to generate a lot more than we use, 120, because they're going to step it down. When they transmit it, they lose a lot of power. So they start real high, but by the time we get to 120, that's what they do. So we got a single phase power in the house, but that's not enough. Well, they're already paying to spin this thing. Now remember, this is on a huge scale. It's not little magnets. The bottom of a dam or something like this. So they go, hey, let's put one 90 degrees off. And so then they'll layer another magnet here. Okay? We'll have conductor wrapped around it. When this moving conductor flows inside of this magnetic flux field, what happens? Produces an electron current. That's what they're producing. Single phase power to us out of phase with each other. Okay? And so when we measure these two wires, the difference, if they're coming into your house and it's 120, then the difference between the two would be 240. If it's 115, putting them together would be 230, if I can add right. And so, but from here to ground, supposedly would be 120 or 125 or 115, whatever our supplier's given. But when we measure across this 90-degree angle, that's what we got. Now, commercials have a 3-phase. And what they'll do is they put these things off 120 degrees, right? 120 would be 360. That's what we got in the circle, right? So this would be here. So we have, I'm going to try my best to draw it like a third. See what I'm talking about? 3 magnets wrapped around. And that's what we mean by 3-phase. But single-phase term seems to confuse a lot of people. They go, oh, no, I got 2 hots. We do. They're 90 degrees off, as opposed to 3-phase. But they don't call it 2-phase. Okay? All right, so before we get into this, let's just talk a little bit more about it. So this electricity, which is simply an energy force that moves these electrons through our conductors, we will design what we call circuits to make use of this energy. Now, the one thing we do is, with this movement of electrons can be very destructive. You know, if you grab a hot power line, chances are it's either going to kill you or blow your hand off or something. But if we can make electrical components that somehow use the power, make use of it, although sometimes we may go, well, that doesn't seem very useful to me, to some engineer it is. If it can make a useful use of it, we're going to call those loads when we're talking about circuits. So in circuits, we have to have loads. If we don't, there's no purpose for the electricity. And we classify these loads into 3 categories. The first would be inductive, and that's a fancy word, and all it means is a magnet, or induction, which is magnetism. And we see this is probably the most common use. If you see a motor, that's using magnetism. If you see a transformer, that's using magnetism. Relays, contactors, they all work through magnetism, which is induction. And so we'll call those inductive loads. That's my first category, right, for HVAC work. The second is what we would call resistive loads. Now, a resistive load means as the electrons flow through this circuit or conductors, there's resistance to the electrons. That causes either heat or light or both. Now, you may think, hey, heating up a wire is not very useful, but when you heat up, a coil to heat your house, it is. Or if you heat up in an incandescent light bulb, the filament, and it glows and gives you light. So those are called resistive loads.
And they use heat.
And they use resistance to the flow of electrons, and they produce heat and light, and or both. Pardon me. And then the third for our HVAC is capacitive loads. Now this is probably the hardest to understand because we say, well, we've got capacitors, right? We've got capacitors. Well, if you look up in the definition or the glossary of your book there, and we look up capacitors, it's going to say an electrical storage device, which is true, but it means nothing to us. What capacitive loads mean to us, because we're not electronics guys, what it means is it's a time delay. Because it takes a minute on a capacitive load to charge it. It doesn't sit there and hold it like a battery till you need it. It charges and discharges constantly. But it takes a flash of a second to charge it. And that gives us a time delay. And we need that in a lot of times we need that in our inductive loads. We, on a scale, we don't really have to worry about the voltage. We see voltage running through its cycle here as it's produced and used, right? This is a circle. We can look at that as 360 degrees. And this power, well, this thing is lined dead up, right? The first one, that's full power, peak power. So let's say, I got 120 volts, although obviously they're not sitting there producing 120 volts. They're producing a couple of hundred, right? Anyway, we'll just say 120 volts, all right? What happens when it spins to here, though? It's not lined up with the magnets. There is no power. Then it goes to the other side. Full power, but in the opposite direction. And then it flips back where there's nothing here, right? No power. And so we would look at that, right, as a 360 degree phase. Okay? And so as we look at this phase, this capacity, what happens on our amp draw? Well, our amp draw is going to get out ahead, depending on how we're pulling our amps. To deal with this phase, in other words, this is later than this, we'll use a capacitor. So what do I have to do? I have to charge it. And it knocks this power into a later phase. Anyway, that's above what we have to know, except for that's why we use capacitors in this business. To line up for that time delay to deal with inductive loads. Okay, so what do we want to talk about next? So those are loads. Now, obviously, you can't have a circuit without power, so I gotta have loads or a load. I gotta have power, which we're gonna call source power, and I have to have a path. And all we mean by path is something to carry those electrons through the entire circuit, right? And that can be copper wire, that may be the connection switch at the light where it closed, there's a path now, it opens, there's not a path now. So we have to have those three essentials in every circuit we work on or design. Now, we can have multiple paths, we can have multiple loads, and that's how we classify. I think in basic electricity, Brian probably spent a lot of time with you on figuring out how to do series and parallel, right? Or combination of those. Or a simple, we simply call a simple circuit one that only has one load. It's really neither series or parallel. So we have to have that, but we do not have to have switches. They make life a lot easier instead of being on all the time, right? But they're not essential. We do have to have a path. All right, so let's talk about, I said I was going to have to go over some of the stuff from components class so we know how to troubleshoot these things. If you look at this handout, if everybody received one of these handouts, right? Yeah, last time. The first thing we want to focus in on, this will be a test question, is on power source. The first page, 298, 26-1.1 power source. The voltage available to the refrigeration unit must be within plus or minus 10% of the unit rating for single phase units and plus 10 minus 5 for three phase. Okay, so how does that affect us? Okay, so if I have a piece of equipment that is rated for 230 volts and it's a single phase, that means the voltage, they're saying this thing's going to work if it's 10% high or 10% low. So 10% of 230 is 23, right? So if I check with my meters, if I have a problem, one of the first things I want to look at is the voltage. Okay? And if it's within 253 or as low as 207, thank you, 207, then it should work. Now, I guarantee you this, it's not going to last as long. You know, say that regular component should last 15 years. It might only last a year. They're saying it will work there, though, at that voltage. They won't guarantee that it won't work at another voltage. I have a variable transformer here, y'all guys. This is old school, trust me. So we plug it up to 120 volts, and it's got a circuit coming out of it. You have to plug it up, it's got a fuse, and you dial in what you want. It goes down from 0 to 140. And so we're using it, it's a transformer, but it's a variable transformer, so we'll talk about transformers later anyway. So in the component class, what we would do is we would take, say, a relay that is rated at 24 volts on the coil. In other words, the magnet at 24 volts will pull in the coil, right? Close or open the contacts it's supposed to. Well, what did we just say? Is that single phase power? Yes. Plus or minus 10% for 24 volts. So that would be what, 2.4 volts up or down. And so we would wire this thing up and see if it would come on up or below that. And a lot of times it will come on, but it won't last as long. A lot of times, if it doesn't have the proper voltage, it doesn't close hard. And so it might bounce. And so you get an arc across it, and you start having arcs across it, that damages those contacts, softens up the metal, and you have a lot of problem. Anyway, our voltage has to be plus or minus 10%. Now let's think about this for a second. When y'all had basic electricity, he probably went over what he called the power formula maybe, or the Ohm's law. And what we had was, I think, E, which he means is voltage, is equal to I times R. And then on the power formula, P, which is watts for power, P over I times E.
So that's E is voltage.
That's right. So voltage, I is amp, this is resistance, P is W, right? So we have a relationship right here. This formula works great on paper. If I manufacture a motor and sell it to you, that resistance isn't changing. On this formula it may change. And so you're saying, hey, this resistance is 100. My voltage is 100. This is just a math problem. So what would my resistance be? I mean, my amp be? Be 1, right? We're saying it has to be plus or minus 10%. What if this drops to 50? My amp's just double, 100% growth, right? That's the problem. Let's show it. What if this went down to 10? My amps down here would go to 10 amps. Y'all, that's a lot more power. That's a lot more heat. It's going to destroy. What is a magnet? Well, a magnet is you take some kind of iron core, like a nail, right? And you wrap a wire around it, an electric magnet, I should say. And we run a battery in there, right? And we're good to go. The more power I run through here, it's going to affect the strength of that magnet and the size of this core. If this thing is designed to run 1 amp through it and we're running 10 through it, you know what's going to happen here? First of all, this wire is insulated. May not look like it, but it is. Painted on enamel. It's going to heat up, it's going to melt off. Instead of going around and around and around and around, and around, it's going to go right across it when it melts. Yeah. Now it doesn't have any resistance. It's what we call a dead short. Destroy itself. Okay? We've got to, a lot of the equipment we deal with, technician will show up, yep, you got a bad contactor, you got a bad relay, and never wonder why. If it's 15 years old, fine. If a technician put it in there a year ago, maybe the voltage is wrong. You know, maybe we ought to take 5 seconds and check the voltage. That's what they're saying. To get the life out of this thing, we expect it needs to be within plus or minus 10%. We call it a cumulative damage when it's running outside of that range, okay? So that's our first rule that we want to deal with power, right? Now, when we have power coming into our residences, and that's what we're pretty much here. If you can troubleshoot a residence, you can probably troubleshoot a commercial, although it's going to be 3-phase, it's going to be higher voltage. And you might run into a few different animals that you don't never regularly see on a residence. Power feeds into a circuit breaker or a fuse box. Okay, so you know some of y'all have been around some of these old houses, or you may live in one that still has a fuse box. It's pretty much, a fuse box is a safety. It's the simplest safety device we have. All right. And you're still going to find them. But hopefully most of the stuff you're going to work on is with breakers, okay? Now when we look at this, and we'll look at this circuit breaker out here in just a second. You know, y'all seen this one out here that's not wired up, right? And so we laid 2 different, remember, we got 2 hots coming in. I mean, although we're calling it single phase, we got 2 hots coming in, and they're overlaid, and a breaker would stretch across both of them. If there's one, if it's only one pole, for 120 or 115, then I don't mean to throw y'all off. I'll begin to say 120 all the time, but y'all do know what I'm talking about when I say 115 or 120, 125. Okay. I'll stop saying that. I'm going to start saying 120. You can say 230. I don't know why I don't say 240. But anyway. Let's take a look. Let's take a look at the breaker first. So, when we're talking about troubleshooting in here, and you may have a problem with the breaker, and we have breakers. We got one right outside that's on inside the ear handler. Usually they give us these whenever you install a heater kit. If it's over 10 kW, they want to either have fuses, which they don't use much anymore, as a breaker. Now, breakers replace fuses because there are two safeties in a breaker. There's two methods, okay? I'm going to read y'all this, okay? Virtually all residential circuit breakers have two independent methods which allow them to automatically switch off or trip. Everybody knows what a trip is? When it trips, you put it in the off position, but the trip is kind of in the middle. But it's off. There's no power. But that way you can recognize it. Instead of going, did I leave that off? And you go, no, that's in the middle. And you can't turn it on from the trip position. You have to continue to off, and then you can reset it. But that's what they mean here. Heat can trip a breaker. When too much heat is generated, usually from amp draw, y'all, a small piece of bimetal inside the breaker begins to bend. This bending force causes the breaker to switch off. This property works well to protect the wire when electrical demand slowly builds. Okay? The second method, pardon me. I don't know if y'all read it, y'all can. However, wiring sometimes short circuits. These short circuits occur when two wires touch each other and generate sparks. Short circuits like this allow massive amounts of electricity to flow through the wire very quickly. Small electromagnets within the breaker sense the flow and instantaneously switch the breaker off before insulation covering the wires begins to melt. And that's what we'll say. You sometimes see that on when you take certification tests. What are breakers for? They're to protect the wires. They're not to protect us. They're to protect the wires, right? So this breaker has two methods of safety. One is from bimetal, right? So when I have two pieces of metal, different, dissimilar metals, fused together, when we apply heat or remove heat, there's a warpage. Metals contract and expand. And so we use a bimetal that cuts the power and an electric magnet. Now, y'all, these are not light switches. I've known people who were so cheap that they use this on their hot water heater because they were leaving the house. When they come home, they're going to take a shower that night, they put it back on or something. That's fine, but this thing is going to wear out, okay? Now, I don't know what they rated at, 10,000 switches, but it's going to, okay? Now, how would you test this? Well, the first test of this breaker would be, does it have power going into it, right? So I'm just going to test coming across it with my voltmeter, right? All right. Do I have voltage coming out of it? I do. Time to move on down the line. It's good. Now, if you don't, you may want to make sure it's set in the on position. Okay? Now, if it's in the on position and you don't have power, what you want to do is cut it off. You want to disconnect the load side, all the load wire. Cut it back on and test to see if you have voltage coming out the load side, right? So let's talk about that for a second.
What does that do on the side?
Do what now?
When you testing it when it's off. Don't you do it? You don't have it. We don't vote. Then do it. When it's in the off position.
Yeah, I want it in the off position, so I can touch it with my screwdriver.
Yeah, no, I'm just want to check the vote. You see, check.
Yeah, once you cut it off, disconnect the load wires, then cut it back on and check for voltage again. If there's a dead short somewhere else, it's going to read voltage. If it doesn't, then the transformer's back. Let's make sure we cleared this up. When power comes in from the street to your service panel, provided by, say, Alabama Power, we're going to call that line voltage. How many lines do most residences have? Two. So you have an L1, L2. Opposite side would be called load. Unfortunately, load starts with an L2. So we're going to call it T1. And if you have an L2, T2. If we had an L3, we go T3.
What does the T stand for?
I have never seen it in the books. Now, the most important thing, though, of this, let's say this is the set service entrance panel into your house. This stands. But let's say you get down to the disconnect on the outside of the house where the unit is. We still use this direction, right? It went into your breaker. The breaker went through the house, went to your disconnect. Now we're going to classify the disconnect the same way. This is line with L1 and L2. This is load, T1, T2, right? So when I'm saying this breaker here, not much of an artist here, right? So this will be my L side, right? So we check for voltage in the on position. If I didn't have it, I'm going to cut it off. I'm going to take these wires loose, put it back on, and check for voltage. If I've got it, you got a circuit problem. If I don't have it, probably breaker here. Now, I will say this. We, as an HVAC contractor, if you're working for one or if you're one, you're not a licensed electrician. And the codes allow us to work to the disconnect. So if you have a disconnect outside, you're not supposed to go any further than that. However, if you're working on the inside where the air hammer is, and instead of having a disconnect, they wired it right into the breaker box, that is your disconnect, okay? Might run into a fuse. Okay, I got a couple up here. You know, we got cartridge fuses of different sizes, screw-in fuses. Here's what we use on the furnaces. These are little car fuses. All right, so all a fuse is the simplest safety device there is, and it works off of an alloy that will melt at a certain temperature rating. Okay. Now let's take a look in your book here, page 300 on this handout. Blown fuse. Y'all see that? Let's go over this. Instant blow or leak type fuses are sometimes used as main fuses. Because they will not carry current above their rating for any length of time, which are in amps, they must be sized to carry the maximum starting current of the unit. This starting current could be more than 150% of the operating current. Therefore, time delay fuses, I'd probably underline that. Time delay fuses or circuit breakers should always be used for refrigeration or air conditioning systems. This will allow closer sizing of the fuse of the circuit breaker to the running current of the unit for maximum protection. So what they're saying is, when this motor starts up, let's say it's a 3-ton compressor, which is going to pull about 20 amps. We usually say about 7 amps a ton. So you need about a 20 amp in there. If it got much over that, I got a problem with my compressor. Let's cut it off, check out my system, make sure nothing wrong. But to start it, they're saying, well, the locked rotor amps, to get it, remember, we call locked rotor when the motor's the sitting there not moving. It doesn't, when we started that, when I was drawing that, it has to start spinning. That's the hardest time. You have to have torque to get it moving. And so they're saying, well, that might be 150% as high. So we may pull 50 LRA or locked rotor amps to get it moving. Well, that fuse blows. Boom. That's no good. So I have to have a fuse that's 50 or 60 amps. That's never going to show up when there's a problem with the compressor. Now it's pulling 30 amps when it's running and it's not starting. We got a problem. So they're saying use time delay fuses if you're going to use fuses, or breakers, because breakers will allow that for a small amount of time. Okay? Now they continue on here. It says checking of fuses is best done by means of an ohm meter. With the disconnect switch open, measure the resistance of each fuse. A reading of 0 resistance on the ohm meter indicates that a fuse is good. Infinite resistance reading indicates an open or blown fuse. Now, this looks like a test question. A resistance reading of anything above 0.1 ohms indicates a burned fuse that should be replaced. Yeah, maybe it's not blown all the way. They're saying it's bad. Now, if you have your meter, cut it on in front of it. Now, y'all, let's talk a little bit about your meters. You have power flowing. Let's say on that line out here, this school has 3-phase power here. There's voltage running through that line. And you may see a bird land on it or a squirrel land on it. I wouldn't recommend you grabbing it. But there's voltage there. Your meter won't read it. The voltmeters we use, these multimeters, are made to read a difference in voltage. Not the presence of voltage. You can get an oscilloscope and several other different things, but these read a difference in voltage. How many test leads do you have? 2. Okay. Now, so how many places can you take a voltage reading across? 2, right? I mean, you don't have 3, you don't have 1. You're reading a difference between point A and point B with your test leads. Now your ohm meter, is it set on ohms? Now, what does it read? Yours says OL?
1.6.
Oh, well, yours says 1.6. We're probably in trouble. Are your leads touching each other?
It's over here now.
Oh, well, now, okay. So, y'all, that means infinite. That means your meter's not strong enough to send a voltage across the air to the other lead, right? It's saying, and the higher, some of you have probably auto range on these meters here. Or you might be able to select a scale, a higher number than a lower number. And this is not a math class. They do go by the metric scale. They'll throw K out on you and M out on you, right? You might want to select a range depending on what you're ohming. But trust me, none of these meters, if they're not touching, are strong enough to read across a gap of air. Okay? And so that means what it's telling you is we don't have a path. That's all they're telling us. We don't have a path. Now, take your leads with one hand, if you don't have gator clips, and put them in your thumbs where the metal's touching in one hand. Just hold them together with your fingers. And what's it reading now? 0.1?
Mine is 0.
Your reading's dead zero? Good.
That's 0.
Alright. This is the bottom for y'all. This is the best connection you're going to get. I've seen guys' meters that read like 0.4 when they're touching. So you're going to, okay, your zero is at 0.4. It's like you kind of have to calibrate in your mind. That's as low as it's going to get, right? We hadn't put a path in there yet. It's got a perfect path, and that's as low as it gets. So what did the paper just say on a fuse?
0.1.
So if it goes,
0.1.
so if it goes above that, they're saying time to get a new fuse.
Yeah.
They're not saying there's not a path. They're just saying that path has a little resistance and it's going to create heat. And if I create heat, I'm going to have problems. Now, do some of you have on the ohm thing, in the ohm area, it may look like a speaker signal. Put it on that one, if it's not on there, and touch them together again. Continuity. Is that yours making sound? I mean, yours? Okay. Now, used to be, man, we didn't have very good flashlights. Now we got flashlights everywhere. All right, continuity may mean I've got a path. I've got a great path, zero resistance. Or it may go, I'm reading 6.4 ohms, but there is a path with some resistance. The only thing continuity, and that's what that symbol means, is there's definitely not an open. If it goes B, it's not OL. And so a lot of times we'd be working in dark places, and we were just ohming out, and as you ohm stuff out, if you could hear it go, B, you knew what you had, because you couldn't see, you couldn't read it. Okay? Very few people use continuity anymore, okay? But it's still on there, it's kind of a holdover from the old timers. So continuity doesn't mean zero resistance. It just means there is a path, okay? Don't confuse the two. Now, if I have a closed switch, I don't want any resistance, right? That's going to be zero, right? If I have an open switch, what should it read? And everything else we're going to call measurable resistance. You know, as y'all do more and more work, you're going to get an idea what things, you know, like a compressor may read 2 ohms, you know, on the star, maybe 3 ohms on the star, and 1.5 on the run winding, and you know, a heater, a 5 kW heater, and you go, hey, that's about 9.5. But y'all don't know that. All y'all know is it has resistance, and so for now, we're just saying it should have measurable resistance. As you get more experience, you may go, hey, I've never seen one that high or that low. Okay? I'm losing my mind. Talking about taking power readings, voltage readings, I guess. Before I move on, I guess I should say, whenever we take an ohm reading, we want to do 2 things first, right? The first is cut my power. You know, y'all are lucky. Most of y'all's meters now are fused. Many students blown up a good meter up, go, man, that was a $300
This
meter.
how you wanna do the what you said?
You want to cut the power. You never want to put it on ohms and put it on a live circuit, okay? If you do, you might be replacing a fuse in your meter. The second is, we're reading from one lead to the other, right? And so it's best to isolate whatever we're reading, because if there's two paths, you're going to read one of those paths. If one's open and you're reading a path you didn't realize, that makes sense. If so we looked at a schematic diagram for a unit. So I had L1 and L2 coming in. Had a circuit breaker there. Comes down here. And let's say we got a fan motor. So we got a compressor. We got a transformer. Okay. You shut this circuit breaker and it trips. Right? And it's going to trip because it's telling me somewhere in here I got no resistance. This power is connecting to this power somehow. Although we have a load in every circuit. It shouldn't, right? You follow me? So I cut the power. That's rule number one on my ohm meter. You read from here to here, and you go, hey, I got resistance. Well, yeah, you didn't isolate. We're actually reading three different circuits. Do I want to read this one? Then isolate it. Do I want to read this one? Yeah, isolate it. Do I want to read this one? Isolate it. Okay? Sometimes that's very simple. There's only one wire on this one so if you pull one wire, you know it's not connected again. The only connection it is through your meter. Sometimes though, there might be 4 wires over, 3 wires over here, so I don't know. Better disconnect them all. Okay. So for our meter here, we're going to cut the power for ohm, and we're going to isolate, okay? Now, as far as taking voltage readings with your meter, like I said, I think I began to say, your voltmeter is there to read a voltage difference, right? Don't ever assume that there's no voltage there. Your meter cannot tell you that. It can tell you that there's no voltage difference, okay? So always, keep that in mind when you're starting to put your hands in there. Do I know how to read my voltmeter? All right, we could go over to that big bus bar over there with the power in it coming in from, and one line of power could be feeding all the buses on this side, the fuses. Let's say it's got a 230 volts and 200 amps on it. And I put my voltmeter on it, one of my leads on it, right? And then I put it on the same wire 3 inches down. There's voltage there, but it's the same voltage. Okay? I'm not saying there is voltage there, but it won't tell you that there's not. Okay? What else do we need to be clear about? Okay, these meters, and you're going to fall, I'm going to catch you in here, working in the lab, and you're going to make a mistake. They're made to be used to take voltage in 2 places. Across the source of power. That doesn't mean I have to be right at the power. power has wire. Maybe it left from there and it's here now. It's left from there and it's here. But I got to be across the source. The only other place I can use it is across the load. Okay? Across the load.
That's why you can't put it on the same bar 3 inches.
That's right. Never in series on the same line, that kind of thing. You can do it, and sometimes it might give you accurate information, but most of the time we don't know if it's giving you accurate information. Now, did I say anything about path? I didn't say anything about taking voltage on a path. And so, a lot of times people think they can accurately use their voltmeter across a switch. All right, we know there's voltage flowing through this switch, or the light wouldn't be on. I know there's voltage there. If I take my meter right now, I'm running down the path. It's going to say 0. There's a good chance when I cut it off, it may say 120. That depends on what? What kind of resistance is on down the line. Okay? So, people fall in that habit. They go to that thermostat. I don't have power. That thermostat. No, they're reading. We got one high in here, 124 high. It's the same leg that comes in that goes to the contactor, to the air hammer fan, to the strip heat. There's not 2 power legs there. Now, nowadays, on these, we've gotten where we started bringing a 24 volt common in. At first, they started putting batteries in these. That's when some people don't like doing batteries, so you can either use batteries or run a common to it. So you got 24 high and a common. Right? Because what does a load need? You got light in here or digital. What does it need? It needs power, that's right. And one leg of power is not good, right? You got to have the other leg, right? Time is starting to drag on now, isn't it, guys?
11:01.
Okay, let's pick up here Monday on the lecture. Let me see if I can figure out how to stop this.